Hi students, welcome to Alpha's e-learning chemistry classes for second year. The running chapter is solid state and now we are in session number 11. In previous session we derived the equations related to packing fraction or packing density in unit cells of cubic crystals. That is nothing but the ratio between the volume occupied by the atoms and the volume of the unit cell. And now in this session, we are going to discuss about the internuclear distance of neighboring ions, not the atoms. Already we derived the relation of atomic radius with edge length with respect to nearest neighboring atoms. There we are getting the atomic radius, but here it is not the atomic radius. In case of ionic crystal, the formulae are in a different manner. And how they differ from the regular and what are the numerical part related to that we are going to discuss in this. And in addition to that, and when we are getting the packing fraction, only some fraction of the total volume available in the unit cell are occupied by the atoms or ions. In case if that means some space, nothing but the empty space or gaps are left. Those gaps are known as voids, and in this session we are also going to cover such type of gaps or voids and how many types they are, what are their position, how they are related to the spheres, that is nothing but the atoms or ions that are already occupied in lattice points. All these we are going to discuss in this session. And first let us move to this edge length and the ionic radius relations in ionic crystals. Before that, just let us recall the edge length and atomic radius relations in different cubic unit cells, what we derived in previous sessions. Let me recollect them. It is nothing but first one is simple cube. In simple cube, the radius is related to edge length as R is equal to A by 2. And in case if it is FCC, that is face centered cubic, then R is equal to A by 2 root 2. And in case of body centered cubic BCC, R is equal to root 3 A by 4. These are the relations between the atomic radius and the edge length. And now if we are considering ionic crystals, then how that ionic radii is related to edge length we have to consider. Altogether, in this case, what we are deriving is D is related to R as R is equal to D by 2. This is the ultimate or the basic formula what we are using in deriving the equation, if you remember. Is it not? First of all, we are finding the distance between the closest neighbors. That distance is D, and then half of that distance is nothing but radius of the atom. Is it not? Now, in these ionic crystals, we should not consider half of the distance between the closest ions, because the two ions are not having the same radii or same radius, because they are different. One is cation, one is anion. These two may not, sometimes it may happen, but in most of the cases these two are not having equal size. And that's why instead of using R is equal to D by 2, we can use 2R is equal to D condition. 2R here means 2R is nothing but RA plus RC. That is nothing but the radius of the anion and cation. That sum is 2R. These two are not equal. In case if it is equal, then it will be 2R. But here we have to consider that 2R is equal to RA plus RC. In such a case, RA plus RC is equal to D. This is internuclear distance of closest or nearer ionic pair. Clear? With this concept, we are going to derive the relation with the edge length. For that purpose, first let us go for simple cubic crystal. Simple cubic ionic crystal. In this case, it is a simple one. As we know, in case of cubic crystals of metals, that is nothing but only atoms present, R is equal to A by 2. But here what we are considering? But we are considering 2R is equal to RA plus RC. So when we are considering R is equal to A by 2, 2R is equal to RA plus RC, we can write this as 2R is equal to A. And in a similar manner, it is RA plus RC is equal to A. This is the relation between the ionic radii of the two ions and the edge length. Here, once they provide the edge length A, and if they are giving RA or RC, the other ionic size we can measure. Simple formulation. It is derived from this. Instead of taking R as distance by 2, here we are considering the inter-ionic distance is nothing but the sum of ionic radii of the two ions. Simply we are getting like this. Clear? And now let us move to the next one. That is nothing but face-centered cubic. Actually here, when we are considering face-centered cubic, we will come across with the two cases. Now let me explain these two cases. First of all, face-centered cubic. Here, case 1 is, actually strictly speaking, face-centered cubic is if one of the ion, let me draw this, if one of the ion is forming or framing the cubic where the ion, one ion is occupying at corners like this, and the other ion is present at face center like this. Then the closest neighbors will be these two ions. These two ions. Are you following? And now, case 2. Let me explain, whereby you can easily understand the difference between these two. Case 2. Here we are considering face-centered cubic where one of the ion is forming the face-centered cube and the other ions are present at other lattice points. Say for example, best example is NaCl. In this case, in this NaCl, chloride is present at corners, and in addition to this corner, the same chloride is present at face center also. That's why this crystal is known as face-centered crystal. Clear? But that is nothing but here I am making this black color circle as Cl minus. And now let me write blue colored circle as Na plus. In this case, when Cl minus is framing or forming the FCC, the sodium ions are present at edge centers like this. At edge centers, and in addition to edge centers, that sodium ions are present at body center. Now, unlike that of this, in this case, the closest neighbors are these two, that is Na plus here at edge center and Cl minus here. These are the two cases. Are you following these two? Just here, one ion is at corner, the other ion is at face center. It is named as face-centered cubic. But here, one type of ion will create the face-centered cubic. And in the remaining lattice points, simply we can say that they are nothing but the voids are occupied by the ion. So in these two cases, first of all, you have to observe in which type of FCC is given. Clear? And in case if it is given as NaCl, that's why in next coming sessions we are going to discuss about different kinds of ionic crystal structures. In case if it is given as NaCl ionic crystal type, then this is the condition what you have to consider. Clear? And first let me explain what is the relation. Now you can simply observe it is nothing but Cl. RCl is here, RCl is here. That is 2 RCl is present in that edge length, and this sodium is also this side RNA and this side RNA. Simply in this case we can say that 2 RA plus RC, that is nothing but 2 RCl minus plus RNA plus. This is A stands for anion, C stands for cation. These two, that is Cl minus Cl minus, Na plus Na plus. Just imagine 2 radii of Na, this side, because half of the distance is radius. Is it not? And here only one radius, here one radius. So total 2 Cl minus radius and 2 Na plus radii. These two is equal to, what is the distance from this side to this side? It is nothing but A, edge length. This is equal to edge length A. This is equal to edge length A. That is the relation here. Or simply we can say that RA plus RC is equal to A by 2. This is the formula related. Now once if they are provided A and one of these two, this other one we can easily calculate. Unlike that of this case, in case 1 where different ions at corner and face center, in this case we have to consider this formula. As we know 2R is RA plus RC. Now first let us write R is equal to A by 2 root 2, and when 2R is equal to A by root 2, and we know 2R is nothing but RA plus RC. So here RA plus RC is equal to A by root 2. That is the formula related. Just to observe here, when one ion is forming corners and face center, different ion, corners one ion, face center different ion, then these two are the closest. But unlike that, in case of NaCl type structure, the same ion is forming corners and face center. In such a case, we have to consider the other ion position which is existing at edge center. This distance is the closest distance. That's why just you observe in the given data whether they are following this type of structure or this type of structure, because this is the concept where most of the students and even for experienced persons are also getting confused. But just if you are following these two systems, then automatically you can eliminate that confusion. Clear? And now coming to BCC, that is body centered cubic structure. In this body centered cubic structure, one ion is forming or framing BC, that is cubic unit, and the other ion is present at center of the body like this. If it is one ion is present at corners like this, at corners, and the other ion is present at the center of this, and now these two, this is the closest distance. Here simply you can consider R is equal to root 3a by 4, or 2R is equal to root 3a by 2. Is it not? And now when 2R is equal to RA plus RC, we can say that RA plus RC is equal to root 3a by 2. These are the different formulae that relates the edge length with ionic radii. If you are thorough with this formula, just what we discussed in all these concepts, just you have to consider 3 points. One is nothing but, in case of metallic crystals, the atomic radii is nothing but half of the internuclear distance of nearest neighbors. But unlike that, here in case of ionic crystals, we can't consider the radii of both the ions equal, and thereby 2R is equal to internuclear distance of nearest neighbors, and 2R is nothing but now considered as RA plus RC. That is one point. And in the second case, when we are following this, we are of getting direct relation from those r is equal to a by 2 or r is equal to a by root 2 or r is equal to root 3a by 4. From that, directly you can substitute 2r is equal to ra plus rc. But that is second point. Third one is most dangerous. In case of FCC, we are finding two types of structures. One is nothing but where one ion is present at corner and the other ion is present at phase center. In such a case, a regular derivation we can observe. But in case of NaCl structures, where only one ion is present at corner and phase center and the other ions are present at edge center and body center, like NaCl structure, we have to go in a different manner. Already I explained that, you have to follow that. Clear? These are the relations between the ionic radii and the edge lengths. And now, for convenience sake, let us solve some numericals related to this concept, and thereby you can get the idea how to apply this concept in solving the numericals when they are asked. Simple numericals that by they are of up to mains and Neet level. You have to solve. Here, one question is given like this. Xenon, it is crystallizing in FCC, that is phase centered cubic lattice. If edge length A is 620 picometers, then they are asking for radius of xenon is how much? It is nothing but it is not ionic, because xenon, only one element is present in the compound, that means in the crystal, that means it is nothing but xenon is nothing but elemental crystal, we can say that. Ions are not present. And now it is given as FCC structure. For FCC, this is problem 1. For FCC, what is the relation between radius of atom and edge length? For FCC, R is equal to A by 2 root 2. Is it not? And now, that A is given as 620 by 2 root 2. That is nothing but 620 by 2 into 1.414. That is equal to approximately 219.2 picometers. Like that. Just we are following this formula. It is FCC. For FCC, already given, it is FCC structure. So as it is elemental crystal, no ions found, and hence we have to follow this. Clear? And now let us move to the ionic crystal models. Problem number 2. In this case, they are providing the radius of Na plus and Cl minus, like this. Here what they are giving the data is problem 2. If the edge length, they are giving edge length of unit cell of NaCl is 600 picometers and RCl minus, that is ionic radius of chloride, is given is 190 picometers. Then the ionic radius of RNA plus is how much? This is the question. And now already it is FCC. How to solve this? For FCC we are finding two types of ionic crystals. One is nothing but one ion is present at corner, the other one is present at phase center. In such a case, Ra plus Rc is nothing but equal to A by root 2. But here it is the different case. Here one ion is present at corners and phase centers and the other ion is present. These two ions are same. Just you observe. And the other ion is present at this condition. Now, these are the closest ions. In such a case, what we can consider, if it is RCl and if it is RNA+. Now, these type sets are 2. Thereby, for FCC, like NaCl, 2Ra plus Rc is equal to 2Ra plus Rc is equal to A. Clear? You can observe. And now Ra plus Rc is equal to A by 2. Now, what is the A value given? Edge length is 600. 600 by 2. That is nothing but 300 is RCl minus plus RNA plus. These two sum is 300 picometers. And now they are providing this value and they are asking for this. RNA plus is equal to 300 minus, what is the value given? 190. That is 110 picometer is the value for sodium radius. Are you following? Actually, it should be A by root 2. In case if one ion is forming corner and the other is present at phase center. But here the same ion is present at corner or phase center and thereby the other ion is present at edge center. In such a case, you have to follow this. Second case it is. Clear? And now, coming to one more model. It is, the data is given for BCC, I think. Yes, it is. Problem number 3. A compound XY crystallizes in BCC lattice. Edge length of crystal is 480 picometers. If radius of Y minus is 225 picometers, then radius of X plus is how much? This is the question. And simply you can follow this. Here it is BCC. And now the solution is, for BCC, what we can consider, generally R is equal to root 3 A by 4. 2R is equal to root 3 A by 2. Is it not? And now, when it is 2R, 2R is equal to Ra plus Rc. That is, Ra plus Rc is equal to root 3 A by 2. Here Ra, that is anionic, Ry minus plus Rx plus is equal to root 3. A is given as edge length is 480 into 480 by 2. Is it not? And now, as we know, root 3 is nothing but 1.732 into 480 by 2 is this total. And they are asking for x minus or x plus or x plus is equal to 1.732 into 480 by 2 minus 225, because ry minus is given as 225. After getting this value, if we are subtracting this, you will get the answer. This is the model, different models what they are asking in competitive exams. Are you clear with this one? And now let us move to the next topic, that is nothing but the empty spaces. The empty spaces that are present when the constituent particles like atoms or ions are closely packed in different unit cells. Here, that empty spaces are known as interstitial voids or spaces. Interstitial voids or spaces. These are of four kinds, four types. One is trigonal void. Trigonal void. Just you remember, it is 2D, two-dimensional void, mostly present in tetragonal close packing. And second one is tetragonal void. Tetragonal void. And third one is hexagonal void. Hexagonal void. And fourth one is cubic void. These are the four types of voids. And just two-dimensional, it is present in two-dimensional void, mostly observed in this type. Here, this void is known as trigonal void. It is not finding any importance in our syllabus. And now, coming to second one, that is tetragonal void. Tetragonal void and hexagonal voids. These two are of having much importance in our syllabus. These two, tetragonal and third one is hexagonal. Hexagonal void. These two are present in FCC or CCP structures. Cubic close packing, or it is also known as HCP, hexagonal close packing, or face-centered cubic structure. And where they are present, how they are present. Just tetragonal void, it is present if it is the cubic. This tetragonal void is present at 1/4 distance on each body diagonal line drawn to opposite corners. Say for example, from this distance to this, here 1, 2, 3, 4, like that. In this case, it is coming like this. At 1/4 distance on these two, and this one, like this. And here you remember, when FCC we are considering number of spheres, nothing but Z is equal to 4. But if you observe, all these are present at body diagonal line, means within the unit cell they present. How many there are? 1, 2, 3, 4, 5, 6, 7, 8. So now number of tetrahedral voids is 8. That means 2 tetrahedral voids for each sphere. These are present. 2 tetrahedral voids for each sphere present. Just you remember, they are present at 1/4 distance on each body diagonal from corner. This is the position. Clear? And each tetrahedral void is associated. Each tetrahedral, that is, each sphere is associated with 2 tetrahedral voids. Clear? And now, how they are present? Just you observe, this is tetrahedral void actually. and with the same it is here this tetrahedral void will present. And now coming to hexagonal void. This hexagonal void is present in FCC, and its presence is at edge centers and at body center, like this. If it is hexagonal, is nothing but hexagon. First of all, this is hexagon. Here the void is hexagonal void, and it is present at edge centers and at body center. If we consider these edge centers and body centers, edge centers 12 into 1 by 4, contribution 3. Body center 1 into 1, that is 1. That is 4 octahedral voids for 4 spheres in FCC. In FCC, the number of spheres are 4 and octahedral voids are also 4. Unlike that, this in tetragonal voids, 8 voids are present for 4 spheres. Clear? And this is about the tetragonal and hexagonal voids. Again I am repeating, tetragonal voids are present at 1/4 distance from the corner on each body diagonal from each corner. Totally 8 tetrahedral voids or tetragonal voids are present for 4 spheres in FCC, and their position is 1/4 distance from the corner. Clear? And now in case of the hexagonal voids, edge centers and body centers are with the hexagonal voids, and as a combination we are getting that 4 octahedral voids are hexagonal, or these are also known as octahedral. These are known as octahedral voids. You can consider like this: hexagonal void or octahedral voids. 4 octahedral voids are for 4 spheres. That means 1 octahedral void for each sphere. You should remember that. And now coming to radius of the void. In case of tetragonal void or tetrahedral void, it is tetrahedral void radius. Tetrahedral void radius by radius of the sphere is equal to 0.225. This is the ratio. Tetrahedral void and sphere radius ratio is 0.225. In case of octahedral void, the radius of octahedral void and radius of the sphere is equal to 0.414. So you remember these two also. Sometimes they may ask for tetrahedral void radius or octahedral void radius. Then if you know the sphere radius, you can calculate this. Are you following? That is about the tetrahedral and octahedral voids. Just here what you have to remember is, in FCC structure, each sphere is associated with 2 tetrahedral voids and 1 octahedral void. Octahedral void position is edge centers and body center. Tetragonal void presence is or position is 1/4 distance from each corner of the cube. And now coming to the last one, that is cubic void. Here simply this cubic void is in contact with the 8 spheres that are present at corners. It is like this. If this cube is having the atoms at corners like this, the remaining space within the body, this total space, is considered as cubic void. Cubic void. And it is observed in BCC structure, body centered cubic structures. Clear? That is about void information. And now related to these voids, what are the numericals? and what are different types of ionic crystal structures that can observe in solid state, we will discuss in the next class.